Phenol. Yeah. So last class, like 2 weeks ago, we were doing preparation of alcohol, different methods of preparation. And last time we did, what did we do? Preparation from hydrocarbons, right? So today, yeah, we'll be continuing from there. We'll start with preparation of alcohols from carbonyl compounds. Okay, what are carbonyl compounds? What do you mean? Like, what do you understand from the word carbonyl?
C double bond O compounds.
Absolutely. So carbonyl matlab any compounds that contain this particular group, C double bond O. So what are the major classes of compounds that you will have from carbonyl compounds? Like what all?
Ketones, esters, aldehydes.
Aldehydes, yes. What else? There's one more major type of compound, which is carboxylic acid. Okay. So from carbonyl compounds, yes, ketones, aldehydes, they are basically the same thing. They contain C double bond O and either hydrogen or carbon chain directly. Esters, carboxylic acids, they have one more extra oxygen apart from your regular C double bond O. Okay. Now, in order to convert this to alcohol, what do you need to do? Like, what part is to be modified or added or removed?
H needs to be added.
H needs to be added. Okay. So conversion of carbonyl compounds to alcohol is basically like you're just reducing all of them. So all of these are reduction reactions. Okay, so you're just reducing carbonyl compounds to alcohols by the addition of H. This would be like the common theme for all of the reactions that comes under this particular thing. Okay. So now let's take it case by case. So A or 1, however you're numbering it. So first part is reduction of aldehydes and ketones. What are the reducing agents that you know of, like based on past reactions and all that? Reduction matlab you need a reducing agent. So what are some common things?
Reduction is the addition of H plus, right?
H in general, H atom. So
H atom in general. Okay. So like hydrogenation, where they use those metals.
Correct. Yeah. So hydrogenation is one method. So be it aldehydes or ketones. So this is an aldehyde, RCHO. So that's C double bond OH, C double bond O with an alkyl group. The reaction is same in both the cases, like the reagent that you use. So one of the reagent is direct hydrogenation, hydrogen in the presence of nickel or platinum or palladium, like catalyst. Okay, so when you add hydrogen to an aldehyde, what sort of a product will you get? Primary alcohol, secondary alcohol, like what will you end up with? I'll like, okay, this is a little vague, so I'll take an example in this case. So if I take CH3, C double bond OH, then just add hydrogen wherever it would be added, like when you're doing the reduction part of it. What is the product that you'll get?
Sorry, I was on mute. Primary alcohol.
Primary alcohol, correct. So what will be the formula I should write? Is it ROH or
R H Wait.
So,
Because that bond will break. There's one more.
so where all will H get added?
One to the carbon atom, one to the oxygen atom. So it'll become CH2OH.
Correct. So you get RCH2OH. So you get a primary alcohol. So aldehydes always gives you primary alcohol because aldehydes are found at the end of the chain. So there's no other carbon atom that this O is bonded to. Yeah, direct. What about ketones? What product do ketones give? Again, for your visualization.
Secondary alcohol.
Yeah. If you have C double bond O CH3, hydrogen gets added over here and to the carbon atom, direct addition then on each side. So what you end up with is basically R remains as it is. This carbon turns into CH2, not CH2. Only one hydrogen is added. And then the other side, R dash remains as it is. And this is connected to OH. So you get secondary alcohols this way. Okay. Other reagents that can be used in place of this, other sources of hydrogen would be NaBH4 and another source popular this thing is LiAlH4. So these are like the three reagents. Either you can use, it's a direct hydrogenation using nickel, platinum or palladium catalyst, or you can use sodium borohydride, NaBH4, or you can use lithium aluminium hydride. Yeah. So three sources of hydrogen. Important part is if you take an aldehyde, you get primary alcohols. If you take ketones, you get secondary alcohol. Fun fact, okay, not fun fact, but when you use lithium aluminium hydride, it is a nucleophilic addition. So if this is a nucleophilic addition, can you figure out what nucleophile is being added? What is the nucleophile we are referring to here? Nucleophile matlab it likes nucleus. Matlab what sort of a charge will it have?
Negative.
Yeah. So lithium aluminium hydride say negatively charged. Yeah, attached.
To be honest, ma'am, all three of them have a valency of positive charge. So,
but look at the context, which is most likely to have negative charge in this context? So, yeah,
hydrogen.
Hydrogen, correct. So, like because hydrogen in this case is bonded to metals, it obviously cannot form a covalent bond. It's going to be ionic when there's metal. Maximum with aluminium, there will be more covalency associated with it. But yes, so the hydrogen from lithium aluminium hydride, LiLH4, it is the H minus that attacks the carbon from the aldehyde or the ketone. So in aldehyde or ketone, you're going to revisit this again when we're studying about aldehydes, ketones, that particular chapter. But yeah, oxygen having more electronegativity pulls towards these electrons. So oxygen has a delta negative, this carbon has a delta positive. So the hydride is going to attack this carbon, and that's how the reaction is going to proceed. Yeah. So yeah, so that's the reduction of aldehydes and ketones. And those are like basic important points in case you need type of reaction. I think NaBH4 also is the similar thing, like wherever you have metal hydrides, it's nucleophilic addition. Hydrogenation is more of a direct, it's like it has its own mechanism, like the hydrogen bond is broken on the catalyst and then it's like a free radical addition. Okay. Ansh and Shantanu, you guys noted it down. If you guys have any questions at any point, let me know.
Ma'am, I've written.
Written? Okay. Shantanu, following?
Yes, ma'am.
Okay. All right. So the next set of reactions, we have reduction of acids, carboxylic acids and esters. Okay. Carboxylic acid is RCOH. So carboxylic acid, again, it's a double duty reduction. Like you have the C double bond O and you have the OH, right? So again, the reducing agent used for this would be really powerful reducing agent. In this case also, you use LiAlH4 and hydrolyze it. H3O plus is required, presence of H3O plus. So this, again, what type of alcohol would you predict from a carboxylic acid?
Primary, because again, that is also the end of the chain.
Yeah, same thing as aldehyde. So you have the R, the C will turn into CH2, and then you have the OH. Okay. So this is again a straightforward, like direct reduction of it, just like with aldehydes. But the problem is that it's not exactly a problem, but the thing is LiAlH4 is a very expensive reagent in general. Like this process of converting carboxylic acid to alcohol using LiAlH4 is an expensive process in general. So that is why this particular process is restricted to laboratory preparation. Like if you want to prepare alcohol from acid in the laboratory, like small quantities, easy to prepare. The reason why you're still using it is this has an excellent yield. It's not, the yield is awesome. Like it converts all of the alcohol into, all of the acid into alcohol. So it has its advantages, but because of cost restrictions, it's restricted to laboratory use, or it is restricted, or it is used in the industry when you need to produce small quantities of valuable substances, like if you want to produce a specific medicine or a drug or hormones, things like that, right? When you want to prepare like really valuable substances in like slightly smaller quantities, that's when you will go for this particular process. That's where it's used. Valuable substances in the sense, something that's not widely available. If you want to synthetically produce a drug or a hormone, things like that. I don't know the specific cases, but that's like the context that I've read about. Okay, so there's excellent yield of alcohol from reducing with LiAlH4, but because it is expensive, you take care of, you're just not gonna use it wantonly. Like you take care of where all you can do it. So a less expensive process of converting alcohols or acids to this thing is to first convert the carboxylic acid into an ester. You guys remember how to convert acid to ester? This was something that you had done way back in grade 10. You remember?
Is it esterification?
That is correct. The process is called esterification.
You add alcohol.
Yes.
After that, I don't know what the product is.
Yes, it is combination of acid and an alcohol. So
And then you get an ester plus water.
correct. The important point of this is if you just mix acid and alcohol, you're not going to get anything. You need to add a little bit of sulfuric acid. So what is essentially happening is that you're removing OH and H. So essentially you're like dehydrating it, and one of the best dehydrating agents is sulfuric acid. So esterification will take place when you mix an acid and an alcohol in the presence of an acid. Usually sulfuric acid is used in this process. Okay, so first convert the acid into an ester. Now this is a process that is widely used because it has a lot of like acid is you get it everywhere. Alcohol, these two you require it anyway. But yeah, like esters have a really large use. Like esters by themselves, you use it in like perfume, fragrance. So
Yeah, they're aromatic compounds, right? Like they have a very distinct smell.
Have you ever used those what do you call scented erasers in your childhood?
Ma'am, it's everywhere.
Still there, okay. Yeah, that artificial sweet kind of smell is because of esters.
So ma'am, I don't know, but okay, so there are these plushies and or like soft toys in my house, okay, and they have a smell on them, and no matter it's been months since we bought the thing, the smell is still there. Yeah, exactly. My sister's holding it and waving the thing right now. So like, and she just threw it. So this is the thing, and it still smells like it has a very distinct smell. Is that the same reason? I don't know. Like it just smells really good. I feel like even if I wash it, it's gonna be the same thing.
It depends actually. Like if it is a very like orange has orangey smell, like lemon has a lemony smell, right? So those flavors
also has some
are due to, you know, whatever this thing is there. But commercially, you have like a generic fruity, sweet smelling things, right? Like which you can't place specifically to any specific, you know, fruit or a flower or something. Then that, you know, that is basically from an ester. If you can identify it with a specific flower or a fruit or something like that, then chances are, you know, like they've taken a little bit of that oil or that extract or whatever.
Okay.
But
just like put all over it.
Yeah. But otherwise,
and it smells really good.
But if it is like a very generic sweet smelling thing that you can't place, then that's probably an ester.
Okay, got it now.
Yeah. And depending on which acid, which alcohol you use, esters are also used in preparing soaps. So they have a wide variety of uses. We'll come to them. We're going to study all about esters later. But yeah, you take an ester, then converting it to an alcohol is again like acid to ester. Again, it's introducing hydrogen to it. So H2, like it's in the presence of a catalyst. So the common catalyst used is copper chromite. So the formula of copper chromite is CuO and CuCr2O4. So this is like the most common catalyst that is used. It's like a mixture of this thing. Yeah, hydrogenation of this, it's gonna like break everything and give you alcohol. So you get RCH2OH, and this other part of it is also will also break down into R-OH. You get your alcohol back, and the acid part of it.
Ma'am, both of them are, one is a primary alcohol and one, no. Both of them are primary alcohols.
Not necessarily. So this part will definitely be a primary alcohol, is connected to the carbonyl part of it. But the other side of ester, it depends on what your RH is. So
okay.
R dash is. So if this part is a secondary alcohol, then here you're going to get a secondary alcohol.
Yes, ma'am.
So this is the commercial way of preparing alcohols from carboxylic acids. Yeah. So either you take an ester directly, if ester is not available, if you have an acid, convert it into an ester and then get alcohols from it. And if you manipulate, like suppose you're starting off from an acid and you want specifically RCH2OH, then you can manipulate, like you can control what alcohol you're taking to make the same alcohols from both sides of the formula. You don't even have to get like different forms of alcohol. So this is giving you a lot more options basically. Yeah. So overall, summarizing, left an empty page here. Anyway, overall summarizing preparation of alcohols from carbonyl compounds, they are all reduction reactions. So you're adding hydrogen, only your source of hydrogen is differing in different cases. In the case of aldehydes and ketones, it's just like one step of reduction. So no matter what source of hydrogen you take, direct hydrogenation or any of the metal hydrides, you are going to get your primary and secondary alcohols respectively directly. If you're taking carboxylic acid or ester, then again, 2 carbon atoms you're reducing to 1 carbon atom. So either use LiLH4 and hydrolysis is going to give you a alcohol. But because this is a more expensive process, another way, the commercial method of preparation is to convert it into an ester and direct hydrogenation of an ester, catalyzed hydrogenation of an ester. Catalyst used is copper bromide. Okay. Then next, the third method of preparation is Grignard reagent, from using a Grignard reagent. Do you guys remember what is a Grignard reagent? Yes, what is the formula? Yes, Natalie got it. Ansh, Shantanu, do you guys remember it?
No.
No? Okay. Ansh, what about you?
RMGX.
Very nice. Yes. RMGX. So Shantanu, Grignard reagent is basically magnesium compound. So just insert magnesium in between haloalkanes. So we did this when we were doing haloalkanes. Need to revise those again. So yeah, so you have an alkyl group, magnesium X. So this is highly reactive. Like you can see that organic covalent compounds would not like to be ionic, but metals are mainly ionic, right? So at like it always breaks down at this point. It is highly reactive, very unstable. So naturally, whenever you want to add R to anything and prepare either alkanes or alcohols or any specific things, or just increase the length of chain, you go with Grignard reagent. Okay. Now in this case, we're looking at preparation of alcohols. So we have our R part of it. All we need to do is add OH to this. So let's see how we can do this. Okay. So with Grignard reagent, our starting point is you take aldehydes or ketones. Yeah, either aldehydes or ketones. So basically compounds with R, C double bond O, R dash. R dash, if it is H, that would be an aldehyde. If it has more carbons, then it would be a ketone. Then when they react with Grignard reagent, RMGX. So this gives an intermediate product called an adduct. So adduct basically is, addition product. You can think of it a shortened way of addition product. So what happens is, the two parts of Grignard reagent are basically added to the aldehyde or the ketone, and like a really complex intermediate product is formed. Now this,
Ma'am,
Huh?
the book gives the figure of this intermediate product. Could you draw it too?
yeah, I will. So I'll just
Oh,
give you the main basic process of the reaction, and then I'll take an example and give it to you guys. Okay. So there's an adduct that will be formed, and treating this with water gives you alcohol, plus your byproducts are MgOHx. So magnesium has a valency of +2. So one is satisfied by the halide ion that's already there, and the other you just have a hydroxide ion. For example, like I don't want to use R dash because there'll be too many R's and it'll get confusing. So I'll take a very specific example for this. Let's take. So I'll take an example of a ketone, and then I'll give one more equation using an aldehyde. You guys try and predict what product you get. Yeah. So let's take CH3, C double bond O, CH3 plus R MgX. Now adduct के लिए, okay, let's look at the movement of electrons. Just focus here for a moment. You guys can note it down afterwards. Yeah. Ansh and Shantanu, you guys focusing here. Now I can't see you because your video is off, but just look here.
Yes,
Okay.
ma'am.
So like the double bond, the pi electrons between C and O, like the extra double bond K electrons, where do you think they will move? Will they go towards oxygen or towards carbon? Yeah, anyone? Like which side?
towards
Side?
oxygen.
Oxygen. Okay. So that means carbon will have a slight delta positive, oxygen will have a slight delta negative. Now look at Grignard's reagent. What do you think the charge separation would be like if this bond were to break? Where would the electrons go?
R.
Towards R. Magnesium is electropositive. It will not get a negative charge. So this will have a positive charge and this will have a negative charge. Okay. So in order to get your adduct, like what do you think would be the structure of the adduct? Which part will be attracted to which part? Like what will be connected to what? So R and MgX, right? So the R, where do you think when it breaks down, when you get R minus and MgX plus, where do you think the R part will move?
To the carbon, the positive delta.
Awesome. So it'll move over here. Yeah, and MgX?
To the oxygen.
The oxygen. So based on this, you can predict the adduct. So your nice. Oh, Mitali, you typed it all out. So you can just change the structure to make it, or I'll just write it like this only. So you have C, CH3 is unchanged, CH3 is unchanged. So niche, the extra R will be connected, put it in a different color. And यहाँ पे this becomes a single bond, and then you have O, and the MgX, this becomes OMGX. Here. So this whole structure is called an adduct. This is the adduct formed in this. This is the reaction intermediate.
Ma'am, I have a question.
Hmm.
Ma'am, if I look at this thing as a just a sec. If I look at this thing as like a compound, carbons four valency. I'm sorry, people just keep coming. Carbons four valencies are satisfied, right?
Yeah.
So like that carbon atom is like the tertiary carbon atom is stable. Then
Yes.
we have O. O also requires two valencies, one here, one there. So technically, even that is satisfied. So like, if this thing is to exist, it can exist, right? Like as this big product.
Yeah, theoretically it is possible. Yeah.
Yeah, but like, why not?
Because again, magnesium is incapable of forming covalent bonds. Like if it would much rather have a simple ionic compound existence, it will always react to that. Yeah. So even the addition of simple water, which is what is the next step. Like once you add water to it, so water is made of HOH. So this magnesium would much rather, take up the hydroxyl ion, and it itself gets replaced with the hydrogen ion from this. So theoretically, it could exist because valencies are fulfilled, but yeah, this part of it is the unstable part. And that's the part that's always going to change. Depending on what, like if you add ammonia or something else, then yeah, accordingly it's going to change.
Okay, ma'am.
Yeah. So yeah, that's exactly what happens when you add water. So the MgX, like the lone pair of electrons on oxygen, takes up the MgX part of it, and the hydrogen attaches itself to the oxygen. So essentially, you're going to get CH3, CH3. Then the R is newly added from Grignard's reagent, and the O is retained from the first this thing, and H is added from the water over here. I just put it in a different color again so that it'll be easy to identify what comes from where. So OH is coming from the water that you add here. And yeah, like your side product, the byproduct is going to be Mg, and the one hydrogen has bonded to the, like it's involved in making the alcohol, and the other one, the remaining OH, is attached to the magnesium. Here. So one special thing that you can see is there's an extra alkyl group that is getting attached to your this thing that's there, that the carbon atom bonded to oxygen. Yeah. So essentially, if you start off with a secondary carbon, you're going to get a tertiary alcohol. So you started off with a ketone, which is basically like a secondary carbon, right? Like it's this carbon atom attached to two other carbon atoms. And the final product, you have an extra carbon attached to it, so you got a tertiary product. So similarly, yeah, there's like if you have a specific raw material and you want to get a specific product, then you have multiple ways of achieving it. So if you start off with a ketone, and if you want to get a secondary alcohol, then you're going to go with the direct reduction process. But if you have a ketone and you want to get a tertiary product, then you have Grignard's reagent. That's an option that you can use. Yeah. So that way, just take care, like just make note of the different mechanisms that it's following, like how it changes the product. All right, so before giving you the next point, I'll let you guys figure out, okay, I'll keep this on display. Tell me, like, what if you started off with methanol? What is the formula for methanol?
HCHO.
HCHO, very good. So that's basically C double bond O and hydrogen on both sides. And your Grignard reagent is CH3 MgCl. Yeah. Tell me what alcohol you get out of this. You can either send the IUPAC name, or if it's easy to type, you can type out the structure also. So all of you, yeah, work this out and send the final alcohol that you get out of this. I'll just read it back. Work this out. Any answers yet?
Just a minute, ma'am.
Nice. Ansh got it. Awesome. Correct. Mitali also got it. Shantanu, you working it out?
I'm typing it.
Okay. Yes, Shantanu, what's up?
I got it, but I don't know how to name it.
Can you type the structure?
Yeah.
Or you can send a picture of your working like notebook may wherever you've done it, click a picture and send it to me on WhatsApp. That also works. So if you're asked to figure out the mechanism, now that we're dealing with MCQs, in case you're asked to, one moment. Shantanu, you're right. So that is the structure of the adduct that you have sent. So if this is to be converted to final alcohol, कौन सा alcohol मिलेगा? But yes, so coming back to it, suppose in your exam, in the MCQs, wherever, if they ask about the adduct in this particular reaction or something like that, then yeah, you need to figure out the mechanism. But if you have to figure out only the final product, you don't really care about the mechanism. Simple hack, not exactly a hack because that's exactly what's happening, is to just so RMGX may the R part of it, attach it to the carbon and then convert the double bond O into OH. That's it. So based on that, you have CH2. So CH2 ऐसे रहेगा, double bond O is converted to OH, and the R from Grignard reagent is CH3. So this will be your final alcohol. Yeah, Shantanu got it?
Yes, I got that answer.
Yeah. So you're partly right. Your mechanism is right. So beach may, that's exactly what you'll get. But for your final product, yeah, in place of MGX, OH. That's your alcohol. Yeah. So based on that, yeah.
Sorry. So when we are doing this thing in school, they made us write dry ether over the thing and said that it's very important. If you don't write it, you're going to lose your marks. So just could you go over the significance of dry ether?
Yeah, that is because again, RMGX ionization, if you put water over it directly, then you're going to end up getting an alkane maybe. Yeah, you get RMGOH and RH. So you don't want any other wayward reactions to take place. You want to keep it dry. You want to force RMGX to interact with the aldehyde or ketone that you've taken. So.
Okay, ma'am. Got it.
All right. So in case you want to get primary alcohols, what should be your starting product?
Aldehydes?
Any aldehyde? Imagine if I take CH3CHO and if I make it react with RMGX plus later on.
Same mechanism will be followed?
Yeah.
Okay. Oh, then it will become like a secondary aldehyde.
This will become
formaldehyde.
So for primary alcohols, the only raw material you can take is formaldehyde, HCHO.
And that's the same thing that we did, right?
Yes. That like this is the only case where you get primary alcohols. So you can control the length of the primary alcohols by taking the appropriate Grignard reagent. So by using this R. But yeah, so this is the only thing that will give you RCH2OH. So if you want secondary alcohols, then what is the raw material you need to take?
CH3CHO.
Any aldehyde basically.
Yeah. Like except formaldehyde. Yeah.
Yeah. Any aldehyde except methanol. And if you want tertiary alcohols, then
Ketones.
you take ketone. That was the first examples that we saw. Because ketones already are connected to 2 carbon atoms, and the Grignard reagent is going to add 1 more carbon chain to it. Yeah. So this is all like the important notes of preparing from Grignard reagent. So we've gone over the mechanism of the reaction. So the first step, yeah, like as you mentioned, dry ether needs to be there so that this goes properly. So the first step, you get an adduct, and which on hydrolysis gives you your alcohol. Okay, and depending on what product you want, you take different types of alcohols, like different types of compounds, aldehydes or ketones. Yeah. Let me know when you've noted this down, and we'll go to the next part. I think we're done with the preparation of alcohols. Now we'll get on to the preparation of phenols.
Yeah, I'm done.
Okay. Ansh and Shantanu, ready?
Yes, ma'am.
1 minute.
Okay.
Yes, ma'am.
Awesome. Preparation of phenols is like pretty important, pretty easy. It's not as detailed as with alcohols. So preparation of phenols, the first is from haloarenes. What are haloarenes? Do you remember? So there are
Had
compounds with a halide.
1 point.
So do you remember which reaction? Oh, Mitali got disconnected. But yeah, do you guys remember which reaction we're talking about here? You want to convert a haloarene into an alcohol. So we discussed this, like if it was haloalkanes, then you go with nucleophilic substitution. So we had SN1, SN2, all of that. But in the case of haloarenes, we said it's not as reactive, except in one case. So chloroalkane, in a very specific condition, can be converted into phenol. Do you remember what is the process for this?
Ma'am, I'm sorry. Could you repeat that again? Because like I got locked out for a second and I couldn't hear you.
So as mentioned, so do you remember the conversion of haloarenes into phenol? We had gone over this reaction in the properties of haloarenes. So it's just seeing if you remember that. So if it was haloalkanes, then you had SN1, SN2, all of that stuff. But here we're talking about haloarenes. So we said that haloarenes are not as reactive towards substitution because
Electrophilic substitution.
they are more receptive towards electrophilic. But this is kind of an exception, like under very specific conditions, this reaction will take place. So this reaction is you treat it with NaOH are standard source of OH minus ions in very specific conditions, which is 623 Kelvin and high pressure, 320 atmospheres. Then you get sodium phenoxide, which is basically a salt. And as always, ionic nature is not tolerated in covalent compounds. So on hydrolysis or acidic hydrolysis or treating with an acid gives you phenol plus NaCl. Here. So yeah, these reaction conditions, treating with NaOH specifically at this temperature and pressure is important. So this is not like a common nucleophilic substitution reaction that happens all the time. Haloarenes, especially like any sort of arenes, are more willing towards electrophilic substitution. They're not willing for nucleophilic substitution. This is the deal. That is the reason last week I asked you guys to revise haloalkanes, haloarenes chapter. You'll find a lot of reactions we'll be revisiting. Yeah. Especially when it comes to properties, a lot of preparation methods of haloalkanes have the source of alcohol. So you're gonna come across them again here. Okay. Then second method of preparation is you have benzene sulfonic acid. What is benzene sulfonic acid? It's a formula. Benzene hai, so obviously you need a benzene ring. Sulfonic acid matlab, what group is it? What should I have?
Wait, sorry, ma'am. SO3H.
Yes. Sulf is basically a circular.
I was like, I went blank for a second. I was like, what?
Correct. So sulfuric acid it's very similar to sulfuric acid, just that one of the OH replaced by your organic part of it. SO3H is sulfonic acid. COOH is carboxylic acid. SO3H is sulfonic acid. Okay. So benzene sulfonic acid. Do you remember the preparation of benzene sulfonic acid from benzene? If you want to add an SO3H group here, what should you treat it with?
Sulfuric acid?
Yes.
I mean, that's literally the most basic thing.
Yeah. So you need to take extremely concentrated, like hard concentrated sulfuric acid. So it's the electrophilic substitution. If you remember, H2SO4 plus H2SO4, you get SO3H plus, and yeah, like one H plus is taken up by sulfuric acid itself. So once you have benzene sulfonic acid, again, the process is same as with the haloalkene, similar. So first treat it with NaOH. So treating with NaOH basically gives you sodium salt of the sulfonic acid, and then on acidic hydrolysis, you get phenol. Again, in this case also, just like the previous thing, your mid product, your intermediate is you get sodium phenoxide. So sodium phenoxide on hydrolysis gives you phenol.
Ma'am, so usually in these reactions, when we're making phenols, there are no like direct reactions as such, right? There has to be like, most of them have like an intermediate step where something is formed, and after that it's converted. So it's like, is it like difficult making it like directly, like just adding water to it?
Yeah, that's the thing. Like, unless it goes through that intermediate, you won't get the product that you need. And in a lot of cases, see, organic reactions are all driven by how the electrons are behaving in that organic compound. Like in the previous thing, especially for aldehydes and ketones, a lot of their reactions are dictated by the fact that there is a delta negative here and a delta positive here. Electrons tend to go this side. So depending on what reagent you introduce, that's going to get attached, one side of it to carbon, one side of it to oxygen. And then again, depending on, whether you put water or whether you put an ammonium salt, or, like depending on what other acid or a base or substance that you put, that's going to decide which direction it's going to go in. So with these reactions, it's not like ionic reactions where you mix these two salts and then you have displacement, double displacement, or anything like that. All of this is like you're manipulating the movement of electrons by changing the environment that this particular this thing is in. So that's how you're getting your required product.
Yes, ma'am, got it.
On social media, I read a very interesting thing. So it's like one of those Twitter. Are you guys active on Twitter?
I am not.
No.
Yeah, surprisingly, I don't have Twitter.
Oh, that's fine. I know, like your generation, I find a lot of you are on Instagram mostly.
Yeah.
Yeah, so there was this thing on Twitter where someone asked the question, like, describe your work or a profession or like particular thing in the most basic fundamental way possible. So for a chemist, it was like you're studying. So basically, electrons are controlling everything. And
Yeah.
people who are doing research in chemistry or doing reactions and studying this field are basically finding a way to manipulate the behavior of electrons, because electrons can like control everything. So that's exactly what's happening here.
It's surprising how it's not surprising, it's astounding that so much of this thing depends on something that is so small, technically insignificant, but not. So that's what I find weird and interesting, ma'am.
Yes. Okay. So that's benzene sulfonic acid. And then you have diazonium salt. Where have you heard of these salts before?
Haloalkanes, halorings, the N plus and Cl2 minus, Cl minus salt. Yeah.
Yeah. So how do you prepare diazonium salt? Do you remember?
I remember, ma'am, because that day I got it wrong when you were discussing. You add it with a very cold mixture of, I think, NaNO2.
Okay.
I think it's sodium plus nitric acid or something like that, something very cold. Then you form NaNO2 or 3, and then you react it with benzene ring, and then it forms
You
something
react
like
it with benzene ring or something else?
Oh no, aniline. Aniline is the starting material.
Correct. Ansh said what he finds weird is that when a chemistry teacher is teaching chemistry, it's just a lot of atoms explaining about atoms. Yes. Okay, so this is how you get a diazonium salt. So treating this, the diazonium part is N2 plus and then Cl minus, whatever ion. Okay. Okay. Now, in haloalkanes, what you guys studied was that once you got this particular intermediate, again, coming back to that, you treat it with CuCl2, Cu2Cl2 you end up with a haloarine. Right?
Yeah.
Instead of CuCl2, if you happen to take water and warm it up a little bit, because this particular thing you're doing it in cold conditions, you end up with a alcohol or phenol. Plus and plus. I changed colors because till here is, like this is how you prepare diazonium salt. And from here, you're going into two directions. Like if you want a haloarine, you treat it with a different thing. You want a phenol, then you treat it with a different thing. Haloarines, like think of it. So there you had Cu plus and Cl minus, and that kind of took place of this whole azo group. In this case, you have H plus OH minus. So the OH minus took the place of this whole entire azo group. Okay. Actually, I'll flip to the next page. Okay, noted.
Yes, ma'am.
Okay. Ansh and Mitali are done. Shantanu?
Yes, ma'am.
And final method of preparation of phenol is from cumene. And this is the industrial method of preparation. Like commercially, if you're getting phenol, this is how it is prepared. So this is like the worldwide production of phenol method of preparation.
Ma'am, I have a question. Is it only me or cumin, I don't know how to pronounce it, sounds like a spice?
Yeah, that's cumin, that's CUMIN.
Oh, yeah. Oh,
That's
I was not wrong. I did not know that cumin was a spice.
jeera in English called cumin.
Yeah.
It's cumin?
Yeah, because ma'am, there was something very familiar about cumin. And during ma'am's lecture, I was just thinking, how are they making it from a spice? How are they making it from a spice? It was horrible.
Well, now it's clarified.
Yeah.
So,
This is what watching too much MasterChef Australia does to you.
oh. So cumene is a tertiary carbon. So this is the structure of cumene. Okay. So you have CH and CH3 and CH.
Ma'am,
Yep.
actually there's there's a parcel that has just come, so I need to go down to get it.
Oh, there's nobody at your place.
No, ma'am.
Okay. Hurry up. Just go, come back.
Yeah.
Okay. So this is cumene. This is the structure. So first you oxidize it using O2, oxygen from the atmosphere, direct, simple. So this gets oxidized easily into, so O2 that is there is added over here. You get a peroxide kind of structure. CH3 remains as it is, and you get OOH. Okay. So this is literally called cumene hydroperoxide. It's easy to see where the name comes from. So the peroxide is basically this part of the molecule. Hydro represents the hydrogen atom on one side, and then you have cumene part of it, which is the other side is full of cumene. Or this part is cumene. Yeah, so cumene hydroperoxide. Then this on, again, acidic hydrolysis. So acidic hydrolysis with a dilute acid, not a concentrated acid. So this turns into OH and CH3, COCH3. So neatly you get acetone plus phenol. So useful byproduct, this thing. So note this down while I see why this is the industrial preparation. Why is cumene? So cumene is found, it's a constituent of crude oil and refined fuels. So that's where you're getting it from. Okay, so if you directly get it from nature while you're mining for petroleum.
So ma'am, it's like during that fractional distillation thing of the crude oil, this is where you get cumene from.
Yeah.
So is it like a top thing or like one of the bottom parts?
Oh, that detail, I don't know. I need to do a little more research about it.
Acha, okay.
But yeah, so that's why, I mean, it's like all of the whole process, you can see that this, you're getting it from crude oil itself. One of the components is easily available. And oxygen from the atmosphere, you can directly oxidize.
It's very cheap. You don't have to put in a lot of money for the raw material because you're literally getting everything from out there.
Yes.
Okay.
Yeah.
That's why industrial.
So you don't need special.
This makes so much sense when you tell us the thing in class. You're like, oh yeah, industrial process. Let's go.
Yeah, textbook doesn't get into the detail of it. Like this puts into context. That's why it makes sense. Yeah. Yeah, but yeah, so that's why it's industrial. Like all of it is easily available. The processing also, you don't need like specialized catalyst or anything like that. So, and the byproduct, this can go directly to nail polish remover industry. This can go to whatever you use phenol for. And that's it for all the preparation methods. It's 4:17. Let me see how many questions we have based on preparation alone. Otherwise, we'll get into the properties also.
Ma'am, I didn't know this, but like till.
All right, physical properties. As usual, let's go over the same. What is the physical state of alcohols? In general, any hydrocarbons, what has been like the trend that has been?
It depends on the molecular mass. If the molecular mass is low, it starts from gas, goes to liquid, and then goes on to
now with
solid.
Alcohol, the smallest alcohols like methanol and ethanol, will they be gases or
liquid? They'll be liquids because they still have like a considerable amount of molecular mass. It's not like it's in what one I was about to say one digit or like 2 digits, but I think it comes under 2 digits. So but like still considerable, they have high molecular mass, more like at least than most of the hydrocarbons.
No, that is not the reason why.
Oh
So,
my god, then I don't
see, if you take methanol, CH3OH, what is the molecular mass here?
12 plus 3, 15 plus 16 plus 1, so 17 plus 1, ma'am.
No, I took 4 instead of 3. So.
Acha, okay.
So this is
so
20.
That's 20, 32.
32, right?
Oh my god.
Compare it to say butane. Or not even butane. Compare it to like single carbon and oxygen, right? Compare it to ethane.
Ethane is C2H6. 24. plus 6, 30.
30, right? But ethane is a gas, but methanol is a liquid, even though molecular mass is comparable. So what could be the other reason why smallest alcohols are liquids? Like you don't find any gaseous.
Alcohols.
Yeah. At room temperature, that is important to know. There will be gases at some point, but not at room temperature.
I don't know, ma'am. Like,
Remember the structure of alcohol. You have R, you've got O, you've got H. And
hydrogen. Oh, no, wait.
yes,
Hydrogen bonding.
hydrogen bonding, correct. So like alcohols are rich in hydrogen bonding. That dictates a lot of the physical properties of alcohols. Yeah. So physical state, yeah, they start off with liquids at room temperature, and then you get solids. The reason is that, again, hydrogen bonding, pretty heavy hydrogen bonding. Yeah. And another thing is that, like, they have a extremely distinct smell. They're not aromatic, but they do have an aroma. Like the alcohol has a smell. Next, what other taste? They do have a distinct taste, described as a burning taste in the book. It burns. So these are like the lower alcohols. The higher alcohols are, I'll just write it over here. When it comes to the higher alcohols, so they are colorless, odorless, waxy solids. So the lower alcohols have a distinct smell, distinct taste, and they are liquids due to heavy hydrogen bonding. But higher alcohols, like as the number of carbon atoms increases, the scope for hydrogen bonding decreases, but again, molecular mass is high enough, which is why they are colorless, odorless, waxy solids. By the way, physical state, samajh mein aata hai, like, okay, these are liquids, these are solids, higher mass and all that. But colorless, like, theek hai, like even the smaller alcohols are transparent, like no color as such. But why odorless? Smaller alcohols, you can smell and taste them, but the higher alcohols are odorless. Why?
I'm not sure, ma'am, but like, what is odor? Like, I didn't even know about the distinct smell. Like,
Alcohols have like a typical smell. Like that's why, like drunk people smell.
oh yeah, that's my acha, sorry. What is the difference between like small alcohols and big
track.
alcohols?
Don't think of it as what's the difference between smaller alcohols, higher alcohols. Think of what is smell or taste. Like, is that like an inherent property, or can that be described only when humans interact with a chemical?
No, because like even if the alcohol is like right in front of me, like just like a glass of alcohol, I think I can still smell it. So I think it's inherent.
How do you smell things? Ansh says after interaction. That is right. Like, how do you smell things?
Can I just come?
Ansh says nose. That's absolutely right. Smell receptors. Very nice, Ansh. It's going in the right direction. So you can smell
receptors.
Yeah.
Oh wait, where are we going with this?
So you attribute a specific smell when the particles of that particular chemical are wafting up your nose, and they interact with I don't know, specific cells or nerve endings, like whatever the receptors that are present. And that is how you taste things as well. Like water is tasteless because, like we are also made up of water. Like it's a thing that's there inside us. But some spices and things are,
They just hit you directly.
because like they create different effects on your tongue. Either your nerves interpret it as we are on fire, or your nerves interpret it as whatever, something else. But it's basically how outside chemicals are interacting with the chemicals in your body, whatever receptors are there. See, so yes, as Anj said, our smell receptors are not able to sense, like basically there is no interaction, like a special sort of interaction that happens with the higher alcohols as opposed to those with the lower alcohols. Lower alcohols, smaller molecules can get into our bloodstream directly, can interact with our human body cells directly, partly because they're smaller and we have a lot of similar components. We are also organic beings, right? So
So, ma'am, higher alcohols can have a smell, but it's just that we can't smell it. Can it be put it
goes
like
into
that? Because that's what I.
because you attribute smells only when you can smell a specific thing.
Yeah, like you said, like it's after the interaction that you can smell a thing. But like
That is
if that molecule is never going to interact with me, then that even if the thing has a smell, I won't be able to realize it.
smell is
So,
literally
ma'am,
perception of thing.
yeah.
It's all chemicals, like it's just how it interacts.
It's like a biology concept, isn't it?
Yeah, more of a biological thing than a property inherent to a chemical. Yeah. Okay. But yeah, like I asked this question because like be aware of how are we getting these properties from. It's literally how your body, like your nose, your tongue, your eyes are.
You should know your body.
Yeah. Yeah. All right, so these are the physical, like what you see it. Oh, and lower alcohols, higher alcohols ho gaya, pure phenols. Yeah, all subjects, like they have their place. Like that is the reason they exist. They have some significance. We study about them. Yeah. Okay, now coming to pure phenols. If they are pure, they are colorless liquids or solids, depending on how heavy they are. But but if they are not pure, they tend to turn brown due to atmospheric oxidation. So reddish brown, it says. And yeah, these are like the basic physical, your senses: sight, smell, taste, related to alcohols and phenols. Then comes boiling point and solubility. So these are the two main properties we'll be discussing. Okay, trend and boiling point. One, we'll check the trend within alcohols, and two, we'll check the trend related to other organic compounds. Okay. All right. Within alcohol, what would you expect the trend to be?
It will be high because of the heavy hydrogen bonding.
No, within alcohols, like if you compare methanol, ethanol, propanol.
Oh, sorry, my bad. Higher the molecular mass, higher the bonding. I mean, higher the boiling point. Sorry.
Yes. So this increases with the number of carbon atoms. Okay. Between isomers, like if there is branching, what happens? These are all the things.
Branching, yeah, decreases boiling point because surface area decreases.
The van der Waals forces. Yeah.
Forces will also decrease, easier to pick the points.
This is like, these two are common things you will come across every single organic compound we're going to talk about. Next.
Ma'am, it's at home.
Yeah, but that was outside my window, yes. Okay. The third part is, compare it to other things. If I compare alkanes versus ethers, because we're gonna study them in this. This is something I think we already discussed at the very beginning. When we discussed about the bonding nature of it, not the boiling points. Okay. And alcohols.
We did the bond angle.
Yeah.
And yeah, I think that's what you did.
Okay. So if you were to compare alcohols, ethers, and alkanes, which one would have the highest boiling point? Which one would have the lowest? So this is RH, this is ROR, and this is RH. Which is the lowest? So that you can easily figure out.
Ether. Zero hydrogen bonding.
What about alkanes?
Oh, alkanes. I thought that was alcohol. So I wrote alcohols, ethers, and phenols. sorry. Alkanes, yeah, ma'am. Alkanes, then ethers, and then alcohols.
Yes. So this would be alcohols. Like let's add phenols also. Yeah. So yeah, the reason is again same as what you mentioned. It is the extent of hydrogen bonding. So reason is the extent of hydrogen bonding. Okay, so alkanes basically no hydrogen bonding because there's nothing electronegative here. You just have carbon and hydrogen. Alcohols, phenols versus ethers. Why do alcohols, phenols have more hydrogen bonding compared to ethers? Like both of them have single oxygen atom only, right? So why is
ethers lack that H atom to make it a hydrogen bonding?
That's right. Yeah.
But there won't be any hydrogen bonding.
Correct. No, this will have hydrogen bonding, but to a lesser extent. So the thing is, a hydrogen that's directly attached to an oxygen atom, there will be a greater charge separation. Right? Like hydrogen, like difference between electronegativity of hydrogen oxygen is a lot more than carbon hydrogen. So this will have greater extent of charge separation, which is why the hydrogen bonding is stronger in alcohols and phenols when hydrogen is directly attached to oxygen. In this case, there is negative charge on oxygen, but hydrogen attached to carbon atoms is not that positive. So the hydrogen bonding also is not that, the difference in charges is not as much. So that is the thing. Yeah. So yeah, simply put, it's basically the extent of hydrogen bonding. Alcohols have largest boiling points, followed by ethers, followed by alkanes. If you compare alcohol with haloalkanes, then which one would be higher?
Ma'am, only with like if it's like if that halogen is fluorine, only then they'll have like a comparable um, boiling point, like somewhere.
That's also debatable because if you look at like CH3F and
Yeah, and CH3OH.
H3OH. So the hydrogen here is again attached directly to oxygen. Fluorine, yes, high electronegativity, but again, these hydrogens don't like they are bonded to
Interact with
carbon.
fluorine.
Yeah, they're not directly
Oh,
bonded to fluorine. So
so alcohols and phenols will have like a higher boiling point due to the greater charge separation.
yes,
So like in the end, it comes down to, like they have a large separation than most of the hydrocarbons out there.
correct. Yeah. Okay. So the ones that would come that are on par with it would be other organic compounds that also have oxygen, and maybe amines to some extent, because even amines, you have the NH bond over here. So again, the charge separation is kind of comparable to it. But yeah, when we study about amines, we get into more detail with this. Okay. So this is the trends, like the points about boiling point / melting point. So you compare the trends within alcohols itself as the number of carbon atoms changes. You compare the trend of isomers, like if they're all the same number of carbon atoms, then with respect to branches, what the trend will be like, and compare it with other organic compounds. If the molecular mass is comparable, if the number of carbon atoms is comparable, then how does it change? Okay. Next comes solubility. Okay. First point, is it soluble or not soluble? Yeah. Ansh and Shantanu, what do you predict? Soluble or insoluble? Nice. That is correct. Alcohols are soluble. And the reason being, organic compounds are generally insoluble, right? So what is special about alcohols that they can dissolve?
Hydrogen bonds.
Yes, that is correct. So their solubility again ties in with their hydrogen bonding. So because they have the OH part that is capable of hydrogen bonding, water is polar. So it basically, there is hydrogen bonding between water molecules and alcohol molecules, making it soluble. Okay. Now, considering the extent of hydrogen bonding, what can you say the trend as the number of carbon atoms increases, what will happen to the solubility? Take the same logic further, like if the R part of it, number of carbon atoms increases.
As the carbon atoms increase, right?
Yeah.
So it will decrease.
Yes, solubility decreases. Because again, yeah, there is only one single OH, but if there is a really long chain of carbon atoms, then it's going to hinder the formation of hydrogen bonds. And what other points do we have? Again, if we have the same number of carbon atoms, now let's talk like if there is branching. So within isomers, branching. Okay, so within isomers, what is the solubility?
And that I don't know.
So let's say we have a straight chain, CH3, CH2, CH2OH, and a branched chain, CH3, CHOH, CH3. Within this, between these two molecules. Hi, Mitali, saw that you got disconnected.
Yeah, I got disconnected. This is the second time it happened. I don't know what is wrong today.
It has been raining, could be network issues. Okay. Yeah, so we're discussing solubility. Alcohols are soluble due to hydrogen bonding. But
Wouldn't solubility be 2?
no,
Achha, no, this was a physical state. Yeah.
okay. And as the number of carbon atom increases, as the hydrophobic part, like something that's incapable of doing hydrogen bonding increases, the solubility decreases. Now, if everything is comparable between isomers, like if the branching increases, then what will happen to the solubility?
Decreases?
Solubility decreases, and what is the reason?
Wait, just a second, ma'am. As a number of CRP. Right.
Let me draw these structures clearly. It'll give you a better idea in comparing. Again, the whole concept revolves around how much of it is hydrophobic versus how much of it is capable of hydrogen bonding. This is one.
Could you define hydrophobic and what is the other thing?
It is
Hydrophilic and hydrophobic.
phobic is phobia. It has a phobia for water. So hydrophobic is does not like water. And hydrophilic is likes water, can mix with water. Okay. So this is the hydrophilic part, and this is the hydrophobic part. In this case also, this is the hydrophilic part, and this is the hydrophobic part.
Ma'am, could you repeat what is hydrophobic and what is hydrophilic?
So hydrophobic is does not like water, afraid of water, does not mix with water. Phobic is like it has phobia for water. Think of it that.
Okay. No, in the carbon chain, hydrocarbon chain, sorry.
Again, simple, logical, right? Like this is the part that forms hydrogen bonding. So this is hydrophilic. And this is the part that is covalent, that does not mix with water. So this is hydrophobic. So the green areas are hydrophobic.
Oh, then it'll be the opposite. Because the surface area of the phobic, the hydrophobic part of the hydrocarbon, if that decreases, then it's pretty easy for the molecule to dissolve in water rather than it being a big chain that is a big hydrophilic part.
Very
and
good.
Yeah.
Correct. So as branching increases, the solubility increases. The reason is that if it's a straight chain, the surface area of the hydrophobic part is larger as compared to for a branch chain. So that in turn affects the ability or the extent of hydrogen bonding again. That's the reason. if you had to put it simply in a single sentence, you can say the surface area of hydrophobic part, or due to the decrease in the surface area of hydrophobic part. Yeah, so these are the basic, like, main points of the physical properties. Talked about the boiling point, we talked about the solubility and general, like, physical appearance, taste, smell, all that stuff. Okay. Note it down, revise it once, let me know when you're ready for the chemical properties. We won't get into the chemical properties. Let's see if we can do at least one. So nucleophile, then we have acidity. Acidity is a pretty large thing. And we have esterification. And then we have, as electrophiles, formation of haloalkanes, mainly dehydration and oxidation.
Ma'am, can we do all the chemical properties like together in tomorrow's lecture?
Tomorrow we'll be practicing, because tomorrow if I take up a new topic, I won't be able to record it, right? So
Oh yeah.
yeah, I'll have
Okay.
to start it again. We'll just do questions tomorrow based on the preparation. So when it comes to properties, right, I'll just give an overview of, like, we won't get into each property one by one. I'll just give an overview of it. So chemical properties are mainly chemical reactions. What all reactions do alcohols undergo? How do they behave with other chemicals? Yeah. So alcohols, you basically have the R group, then you have O group, like oxygen, and H. OH is the alcohol thing, right? So multiple ways it behaves, like in different contexts, different thing. So one is where you have OH bond breaking. So the RO, like alkoxide part, is part of a new product. So when OH bond breaks, like, basically, again, oxygen will always take a negative charge, H will take a positive charge, right? So that contributes to the acidic nature of alcohols. So we'll discuss in what context do they behave like acids and how much is their acidity, strong or weak, all of that stuff. Phenols have a special role in this. Phenols tend to show a lot more acidic
Like
nature.
the electron withdrawing group, releasing group,
Yeah.
and all that.
Electron withdrawing group and resonance, both of it helps with that phenoxide ion. And another thing is esterification may, like, so the OH from the acid breaks off and the H from alcohol breaks off. So this bond break happens mainly in esterification reactions.
Ma'am, there were bond cleavages as well, right?
That's what I'm talking about. Bond cleavage of OH bond. So these are the two
Okay.
properties we'll talk about. And another set of properties is bond cleavage of the CO bond. This has, like, multiple reactions. So you have formation of haloalkanes. So basically you substitute OH with a halide ion. So there you have multiple reactions. You studied it in preparation of this thing also. So hydrogen, like, you can do this with HX, you can do it with phosphorus, like PX3. All of these is there. Then another main reaction you have is dehydration reaction. So dehydration may you lose the OH along with a beta hydrogen. So that will give you alkenes. And you have oxidation. So oxidation may, so no, this won't come under oxidation. Oxidation is completely different because
It happens in phenols, right?
You have a double bond being formed over here. So oxidation will not come under this set. That's a completely different set of properties. And then apart from that, you have oxidation.
So ma'am, these are both the bond cleavages are common to alcohols as well as phenols, right? And then there are separate 5 reactions that we study under phenols.
So RO bond, this phenols will not undergo because it's really, really difficult for the CO bond to break for phenols.
Partial double bond characteristics.
Yeah. So these two you get for phenols also. This you don't get for phenols. No phenols. Oxidation and the whole other set of reactions for phenols, you have like electrophilic. So again, other set of reactions of phenols has to do more with the aromatic nature of phenols. So you have electrophilic oxidation. Yeah. So those reactions only phenols undergo because of their aromatic nature. You don't find them.
Ma'am, can we do like MCQ questions as well tomorrow, like separate MCQ and assertion reasoning questions?
Yes.
On the things that we've covered so far.
Yes.
Okay, ma'am.
Okay. So Ansh and Shantanu, revise all of the whole chapter that we've done so far. So all of preparation of alcohol's part of it. Okay. It'll help. We can jump right into the questions tomorrow. And Shantanu, I would like just go over haloalkanes, haloarenes part also. So if there's any specific mechanism you're not sure of, any like within alcohols, within this chapter, any part you want to repeat or something, we'll do that in class tomorrow.
Ma'am,
Okay.
will you be doing questions on the whole chapter up until now or just the alcohol part of it?
We did only alcohols till now. About phenols and this thing, if it relates to trend of the properties like bond angle, solubility or boiling point, things like that, I'll definitely take that up. Preparation of phenols also we have done, so that also I'll take that up. It's
So
going to
ma'am,
be
basically alcohols and phenols until the chemical properties of it.
till before
Okay.
chemical properties. We haven't done chemical
Yeah,
properties.
Yeah, we did preparations for both of them together. No?
Yes.
So.
Yeah. So alcohols and phenols, all the preparation methods.
Okay, ma'am.
Yeah. Revise it and yeah, come prepared tomorrow if you guys have any specific things you want to discuss, so that we'll get time.
Okay, ma'am. So what we're supposed to do as thing for prep for tomorrow is that study all of the preparation methods for alcohol as well as phenols, including the physical properties of both of them.
Yes, revise the whole chapter, whatever we've done till now.
Yes, ma'am.
And I'll send you guys the topic practice questions anyway. And yeah, you can go through the questions, you can try solving it. We'll do that same thing tomorrow anyway. So
Yeah, ma'am. Okay. Thank you, ma'am. Have a good day.